the semester gets kind of rough. All right. So we are going to talk about another aspect of gases, another type of gas problem called partial pressures, or related to partial pressures. And to me, the reason we get partial pressures is because gases are they have all this kinetic energy. They're moving around. In this room we have, it's about 80-20, nitrogen, oxygen. Those gas particles are just filling this room. It's a gas mixture, okay? So it's not like a solid. Like if you have a solid A plus a solid B and you put them in a container, they just sit there, right? Liquids, they might, depending upon their viscosity, go ahead and mix. Gases, they're all over the place. I just love it, okay? So whenever we have a gas mixture, basically within that container, we have those two gases kind of behaving independently of the other gas that's there. So they have individual partial pressures, but they collectively exert what we're going to call a total pressure. So we have a couple of gases here. We have hydrogen and helium. The P subscript, the P is the partial, so P subscript H2 is the partial pressure of the hydrogen. P subscript HE is the partial pressure of the helium. And kind of like we've done before, picture them in containers, and that lid, that kind of gray, is almost like a piston. It can move. And so it's held in place by the number of weights that are on it. So just by the fact that there are 5 weights over there on the helium, that's more pressure that those helium gas particles are exerting versus the 2 little weights for the hydrogen. Okay, and so we actually have the moles given and the partial pressure, 2.4 atmospheres and 6 atmospheres. So if we go ahead and keep the same container volume, so all 3 volumes are the same there, but what we've done is, one way or the other, taken the hydrogen and the helium and put them in the same container. Okay, the same volume. Not so surprising now. On that little piston thing, we need 2 plus 5, or we need 7 little weights. Okay, isn't that kind of cool? Visual. And so honestly, the total pressure over here of this gas mixture, hydrogen and helium, is 2.4 plus 6, 6.4. Oh, sorry, 8.4. All right? Visually, that's what we have going on there. And I guess the volume is the same. It's quantified as 5.0 liters all across the board. Okay? So kind of similar, we're going to do a little thought process. We're going to have 3 gases, gas A, B, and C. Okay? And notice that these little cool glass jars, that's the one thing about chemistry I like, is I love glassware, okay, and solidware is not so fun. But so they all have the same volume, and the gases are going to be hanging out all at the same temperature. Of course, N is the variable for moles. So we have a certain number of moles of gas A, a certain number of moles of gas B, and gas C, etc. Those cute little circles at the top there are actually the pressure gauges, kind of like you see a pressure gauge go like that. It's deflected the greater the pressure. Okay, so we have what we would say a partial pressure of component A, partial pressure of component B, and component C. These are 3 different gases. Now, you can rearrange PV equals nRT, solving for P, and it looks like this. The pressure of anything is equal to the number of moles, RT, divided by the volume. So the partial pressure of A is equal to the moles of A. Okay? Partial pressure of B is equal to moles of B times R times T divided by B, etc. All right, so you know what's going to happen, kind of like we did with the hydrogen and the helium. We're going to somehow go ahead and get these 3 gases into a 4th container that has the same volume. Okay, it's hanging out at the same temperature. We're going to get all those moles over here. The total number of moles that are going to be in here are going to be the moles of each of the individual gases. Okay, and that little gas gauge at the top there, kind of like the hydrogen and helium mixture, is going to be reflecting the total pressure, okay, of all 3 gases in there. So that total pressure is equal to the total number of moles times R times T divided by V. Okay, so that's kind of what we have going on here. So kind of like a little proof, we could go ahead and expand that one scenario. We have all 3 gases in the same container. Break out, and the total number of moles is equal to the sum of the 3 individual moles. using the distributive property of math, okay, go ahead and break out this addition in parentheses. And we could actually break out and have three terms, which you probably recognize as the partial pressure of the individual gases. It's just a little proof, just to kind of get the juices flowing with regard to partial pressures in gases. It's a wonderful thing, and it's called Dalton's law of partial pressures. It's on the next slide. This is what this is. It could be in your notes that you don't have this little T here for total. When I work with these problems myself, I usually use a capital T, but it was just easier in my lecture slides to use a lowercase t. But if you want to add that, you can. So what Dalton says, and it is the same Dalton who did atomic theory, I think, right? Smart guy. He was colorblind, I believe. Okay? What he says is if you have a mixture of gases all in the same container, then their pressures are additive. So the total pressure that the gases are exerting is equal to the sum of their individual partial pressures. Makes sense. But we kind of, a few slides ago with the three components combining into one common container kind of proved that, I think, in case you needed proof. There's another cool thing that we can do with gas mixtures. So if we have a component A in a gas mixture, okay, this would be its partial pressure. Okay, this would be the total pressure for that gas mixture. One of the things we do in physical science a lot is to go ahead and take equalities like you see here, an equality and an equality, and basically divide each by each other. I'll show you what I mean. Okay, so if you take this equality, partial pressure of A, and if you divide it by this equality, the total pressure, okay, the beauty is, and you're going to see on the next slide, is that the temperatures, the volumes, and honestly, the ideal gas law constant all cancel out. So you're going to see here in a minute this thing reduced as a ratio, partial pressure of A to total pressure is equal to the number of moles of A to the total number of moles. It's a wonderful thing. That's not the form we usually use it in. We clean it up because usually you know the total pressure. And there's a good chance that you know the number of moles of a component and the total number of moles. And oftentimes you're after the partial pressure. So if that's the case, if you're after the partial pressure of a component, all you got to do is you got to know the total pressure of your gas mixture. And basically what this is, and it's right down here, what you need to know, and I think we talked about mole fractions before. Maybe, maybe not. That might be Gen Chem 2. One way to talk about the concentration of a component in a mixture is to talk about the number of moles, that's N, of the component to the total number of moles. So that's called mole fraction. That's pretty good. We'll kind of play around with that. The symbol for mole fraction is X with a subscript for what mole fraction of what. So the mole fraction of the component A would be X sub A. So we can go ahead and swap that out, and this is actually kind of a cleaner version of how could we get to the partial pressure of a gas component if we know its mole fraction and if we know the total pressure of the mixture. This is how we can do it. Handy dandy. So let's work a couple problems, shall we? I don't think I'm even going to draw a box. I think you guys are capable of picturing a box up there, and we have three gases. When you're working problems in chemistry, don't get in blinders on and think, oh, I'm working gas problems. I know these are gases. Not necessarily. So these are all gases. They're bouncing around the same container. They have the volume of the container. You have the temperature that they're bouncing around at. Okay, of course, if you're using P equals nRT, you're going to have to put that 15 degrees Celsius in the Kelvin. So there's definitely more than one way to skin this cat, but you're supposed to come up with the partial pressures of each of the three components, carbon dioxide, nitrogen, and neon, okay, and the total pressure. So one good way to, or one thing I think you're going to have to do is knock out from those grams to get to the moles of each of the components. So you were given 2.00 grams of carbon dioxide. You would need to come up with the molar mass of CO2 using the periodic table and use that as a conversion factor. Three sig figs, nitrogen, 2.00 grams, periodic table, one nitrogen is 15.01, so molar mass, and N2 is 28.02. 3 sig figs, that's the moles of nitrogen. And last but not least, unless you have the average atomic weight or the molar mass for neon memorized, you need a periodic table for that. You can convert that 2 grams of neon into moles of neon. So I was trying to remember how I skinned this cat. The next slide you can already see is basically we can take these individual moles and come up with the total number of moles. You wouldn't have to do it that way. We don't do as much addition as multiplication and division in chemistry, but since we're adding, we round according to decimals, and we have 4 decimal places here. So that's why now it's like, wait, you have 3 sig figs in each one of those terms. Yes, but we're adding, so we keep all of them. Okay, so that's NT, N sub T. All right, so we can get the total pressure, which was one of the questions, wasn't it? We can get the total pressures by taking that number, that total number of moles, times R times the temperature. Remember, we're going to have to convert from Celsius to Kelvin, divided by the volume, which I think was that 5.00 liters. Total number of moles, 0.2159. Temperature, converting 15 degrees Celsius to Kelvin is 288 Kelvin. Again, the volume is 5.00 liters. So once you plug in for the total pressure, number of moles, the ideal gas law constant, the temperature in Kelvin, and the volume, rounding it to 3 significant figures because the limiting term looks like our temperature. The total pressure is 1.02 atmospheres. You know, this is a better route to go, I think, because alternatively we could have used this 3 times and come up with the partial pressure of each of the components. You know, it's more work. So, but to get to the partial pressure of each of the components, now we're going to use that relationship a little bit ago. The partial pressure of a component is equal to its mole fraction times the total pressure. Okay? So, picking on carbon dioxide. The mole fraction for carbon dioxide is the moles we got, 0.0454, divided by the total number of moles, 0.2159 times the total pressure, which we just came up with. Rounding it to 3 sig figs, partial pressure is 0.214 atmospheres. So the partial pressure for the other 2 components is going to be very similar. The only thing that's going to change what is that number in the numerator. Makes sense? So for the nitrogen, we came up with the individual moles of nitrogen, 0.0714 moles divided by the total moles, 0.2159 times the times the total pressure. And last but not least, neon, we said it contributed 0.0991 moles divided by the total number of moles. That's the mole fraction, that's X, and then times the total pressure. And if you're one of those, I don't know what sort of personality it is, but you'd already be adding up these 3 individual partial pressures because you're like, dang it, it better add up to be 1.02 atmospheres. And you're right. Okay. That's it. Not too bad. Okay. Any questions about that one? I'm debating about, I think I will. Let's take a look. We're doing really good for time. We'll be out of here early. Let's take a look at, no, that isn't it. There's 2 homework problems that go along with this, and then there's 2 homework problems that go along with the second part. So just to kind of put it in context, you have, I think it's 60 and 61. They go along with what we just did. They aren't too bad. It basically says you have hydrogen and helium as your mixture. It gives you mass, so you know you're going to have to go to moles. It's very similar to what we just did. I'll put the whole thing up here, I think, if I can figure that out. Oops, sorry. So it's not too bad. It's basically what we just did. You're going to use the mass to get to the moles and of the individual, the hydrogen and the helium, come up with an NT value, okay? Plug it back in to solve for the total pressure, okay? And then go ahead and take the total pressure times the mole fraction of each component to get to the partial pressure of each component. That's okay. The next one is similar, okay? But in this case, I guess it is a little different. We have 2 components, but it's kind of, to me, done stepwise. They say they have a container, and they give the volume of the container, and they say it's filled with argon. They give the temperature and the pressure of the argon. And then they say, to me, the stepwise process was, then they add benzene, and at that same temperature and pressure. So what I would suggest doing is getting the number of moles of argon, because first, getting the N sub argon, the number of moles of argon. This is only one way to skin this cat. There's many ways, from the pressure, temperature, and volume. And then recognize they give the mass of the benzene, that 0.278 grams of benzene. Of course, you'll have to use the molar mass to get to the moles of benzene. Okay, and then you can add those 2 together to get to the total number of moles. Okay, but I see here, I went ahead and got the pressure of benzene instead of doing it that way. Instead of getting the total number of moles, I went ahead, and now that you have moles, of course you have the volume and the temperature, you can get pressure. And then you can add those 2 together to get the pressure, which again, is probably, I don't know if that's the best way to do it. And the second part of the question said, what are their individual pressures? And if you worked it this way, you already have them. So, I don't know. It's funny. Not really funny, but depending, I know I don't work the same problem the same way from semester to semester. Okay. So, back to this problem, okay? So 2 more problems that are due Wednesday. Okay, dimethylhydrazine, and I looked it up because I'm like, hydrazine, we've looked at hydrazine before. Basically, it's got a nitrogen, single bond nitrogen, and 2 hydrogens branching off of the each nitrogen, and it does have a pair of lone pair electrons, because I'm like, that's not a complete octet. Okay. Well, in this case, 2 of those hydrogens on one of the nitrogen have been substituted by methyl groups, so thus the dimethylhydrazine. Dinitrogen tetraoxide. Notice that we didn't do anything with covalent compounds with naming things. When you name these things, then you get to use the prefixes, the tetra, tri, di, etc. Anyway, okay, so it says it gives you the mass of the dimethylhydrazine. So I would jot that 1.50 grams, sorry, 150 grams. Okay, and it says that we have the dinitrogen tetraoxide in excess. Lucky us. Okay, it gives a temperature. We could go ahead and convert that to Kelvin. And it gives the volume. And, oh yeah, now I remember this. This is a case where we have 3 products, and each of the products are in their gas phase. How do we know they're in their gas phase? Because the little G after them. So basically, it's a big tank, isn't it? 250-liter tank is going to be filled with those product gases. Okay, and we are supposed to come up with, so if we were, because I told you the other day, okay, I told you to go ahead and say, what's the pressure, what's the volume, what's the number of moles, and what's the temperature. Okay, actually we're after total pressure, excuse me. And the volume is that honkin' 250 liters. Number of moles, we could get that from stoichiometry. And we are, in a sense, I'll put that from stoichiometry. And of course, the temperature, we can get the 27 degrees Celsius to Kelvin, no problem. You'll be doing that in your sleep. So we're after the total pressure, okay, and then we're after the partial pressure of one of the 3 products, nitrogen. So we can do that. Now, we could do this the long way, but I'm going to show you how to not do it the long way. Well, one thing we're going to have to do, and that's what this one slide does, is go ahead and convert that mass of the limited supply reactant, the dimethylhydrazine. We need to go ahead and use its molar mass to get to the number of moles of hydrazine. It's pretty straightforward. And we could go ahead and use those. We could use the stoichiometry of the balanced chemical equation. We could use 3 stoichiometric ratios for each of the 3 products to get moles of each of the 3 products. Okay, we could do that. Or we could recognize that for every 1 mole of dimethylhydrazine, okay, you form a total of 9 moles of product gases. If you add the coefficients of 3, 4, and 2, and from the nitrogen, the water, and the carbon dioxide gas, that's 9. So you get 9 moles of product gases. For every 1 coefficient in front of the dimethylhydrazine is 1. For every 1 mole of your limited supply reactant. So now let's go ahead and run with that. So we're going to go ahead and carry over the moles of the dimethylhydrazine we have in that given mass, plug in the stoichiometric coefficient, ratio. Plug in that stoichiometric ratio. So this is our NT. That's our total number of gas. Total number of moles of gas. Isn't that slick? That's a lot of moles of gas. So if that's our NT, our total number of moles of gas, we can go ahead and knock out the total pressure. So the total pressure will be the total number of moles, that 22.5 moles, times the ideal gas law constant, 0.082058 liters atmospheres per mole Kelvin, times the temperature, the Celsius temperature we fixed is to Kelvin is 300 Kelvin with 3 sig figs, divided by the volume of the container, which is 250 with 3 sig figs liters. So that's the answer to the first question. What is the total pressure? That's it. So to get the partial pressure of nitrogen, which is the next thing, all we got to do is somehow calculate the mole fraction of nitrogen and multiply it times our total pressure. So if we go back to the stoichiometry, oh yeah, that's right. We already know from the stoichiometry what our relative mole fraction of nitrogen is, because we know we're going to get 3 moles of that particular gas for every 9 moles of total gas. Coefficient for nitrogen, 3. Coefficient total moles of gas produced, 9. So 3 to 9 is actually our mole fraction. 3/9 is going to be right there. Again, there's all twists and turns, right? Some chemistry problems are worse than others. There are definitely different ways you could go about this. This is probably one of the most streamlined ways of getting there. So the mole fraction of nitrogen is 3/9 times the total pressure, 2.22 atmospheres. Rounded to 3 sig figs, the partial pressure of the nitrogen gas is 0.740 atmospheres. And that's it. But there's one more problem there. Okay. That's not it, is it? Well, where was, oh, I know. I was like, wait. Okay, so, yeah. I'm going to, my notes, how do I say this? I'm glad I'm going to touch base with problem 67 and 68 with you, because my notes probably need to go into when you collect a gas over water. And your textbook, I looked at it while I was at my desk a little bit ago, your textbook does a good job of talking about this phenomenon. That's not the one I wanted. I did it twice. Oh yeah, there you are. All right. So there are 4 problems that are due, and these are the other 2 that are due. So you basically have solid aluminum, and it's your limited supply reactant, excess HCl, and you can see that since we're studying, doing gas law problems, the gas of interest is hydrogen. But the problem describes it as collecting the hydrogen over water. And your textbook has, I think, a pretty good figure. Okay? This figure right here, kind of both of these figures from left to right, are showing you a gas being collected over water. There's 2 figures here because they're kind of showing you progression. Basically, you have a container outside, I think they call it the gas generating. Okay, in this case would be, you probably have excess HCl here, you kind of have powder aluminum, and then this actually is a solid top, solid except for a hole. It's a single hole where it has a glass, you can put like a glass tubing, and then you can have rubber tubing connect up here. Okay, so basically, you know that once you mix that aluminum with your HCl, and you guys are doing this in Thursday's lab, by the way, it's not aluminum, but it is magnesium. You're going to admit magnesium into HCl, and it is going to fizz. And you are going to collect your hydrogen gas over water, too. The thing about collecting hydrogen gas or any sort of gas over water like this, there's a few things. One is that your gas of interest, and I've kind of got green hash marks here, your gas of interest is not going to be just your gas. Actually, it's a gas mixture. It's got your gas of interest and it's got water vapor. This table right here says how much water vapor you can expect to be hanging out. This is the water vapor pressure at a particular temperature. Okay, so in this case, they say the whole thing is going on at 25 degrees Celsius. Your water vapor is running about 23.76 millimeters of mercury. That's your saturated water, your H2O gas in here, in addition to your H2 gas. But, like I said, I like what your textbook, because it reminded me how this works. They also give the barometric pressure, the room pressure. And whatever the weatherman tells you, that's the barometric pressure. And the way this whole thing works is basically the pressure inside, which is these 2 components, is equal to your barometric pressure. Barometric pressure is equal to your water vapor, in this case, plus your gas of interest, H2. Well, it'll always be water vapor, but your gas of interest, H2 in this case. We can rearrange this to get the partial pressure of H2 by taking the barometric pressure, which was 744 millimeters mercury, from that subtracting the partial pressure of water. In millimeters of mercury, it's 23.76. So it's kind of a front end sort of thing. But once you do that, it kind of turns into something that you've seen before. What is the volume of the mixture? And so the volume that is containing your gas of interest and your hydrogen and your water vapor, which just happens to be there because of how you're collecting it, that volume is the same for your H2, which we're honing in on, and your H2O. They share the same volume. They're kind of independent of each other, but they share the same volume. Okay, so that's what you're solving for. I said the partial pressure of H2 you can get by difference. Okay, solving for volume. You can get the number of moles of H2 produced from the mass of your aluminum, and of course your temperature was given in Celsius. I don't know why they do that, so you got to get it into Kelvin. Okay, so it's not too bad. Once I explain that other part. That's why I said I probably need to amend my notes and add this. So here again we have oxygen gas. It doesn't say how it was generated. It just says that it's collected over water like this. And they give the barometric pressure in the problem. And they go ahead and they give you the blue table I saw a minute ago. They go ahead and give you the corresponding partial pressure of water at that particular temperature. So by difference, you can go ahead and get the partial pressure of the O2, which actually is part A. Part B says what is the volume percent. And the beauty of this is volume and pressure are directly proportional. So basically, to get to volume, the volume of O2 to the total volume, okay, you can go for the partial pressure of O2 to the total pressure. So it's really not too bad. Don't make it hard. And then to get parts per 100, multiply it by 100%. And then C, how many grams? Actually, C is the only one you're going to have to use the ideal gas law equation. Because by this time, you can get to, you're after grams, but you can get to N by using P equals nRT, the partial pressure of the O2, the volume of the O2, R and T. And then you can use the molar mass of O2 to get to grams. That's it. Okay? I already showed you the other two. I'll post these, and when we meet Wednesday, it should be a short lecture. And our usual study session Wednesday after class.